Today we are going to talk about vectors. Vectors is something that is very, very important this entire semester. We will very rarely stop doing vectors. We'll have a few breaks from vectors this semester when we do energy, for example, but most of the semester is going to be heavily involved in vectors. Given that, I think that it's a good idea today that we go over vectors to some extent. And so you can follow along with me in the 03 Vectors PowerPoint presentation, which is on the Files section. Vectors. I wanted to first show some of these things from last time. The unit prefixes. I do want you to know the unit prefixes. That's very, very important to get the unit prefixes remembered and know how to use them. Know that, okay, 10 to the negative 6 is micro, and okay, so if I have 80 micrometers, then I can just say 80 times 10 to the negative 6. Things like that. That's what you need to be thinking about when you do this, when you use unit prefixes. Also, I wanted to remind everyone about significant figures. Just use 3. Just use 3 sig figs, 3 or 4, and I'll be more than happy with that amount of sig figs. Okay, vectors. To understand what a vector is, we first have to understand what a scalar is. A scalar is anything that just has an amount or a magnitude without a direction. So things like time, mass, dollars, distance, those are all scalars because they don't have a direction. We talk about going back and forth in time, but you can't go sideways in time. So you can have positive and negative amounts of these things. Hopefully you don't have negative dollars, but whatever. But you don't have left and right versions of these, except kind of distance. But when we talk about just distance, we say, oh, it's 300 kilometers to Miami. If you wanted to talk about the direction to Miami, that would be a different thing. It's 300 kilometers south to get to Miami. So the difference between distance and displacement, that's a difference between distance and displacement there. The distance to Miami is 300 kilometers. The displacement is 300 kilometers south. You see maybe a pattern there, that a scalar is just going to have an amount and a unit, 300 kilometers. But a vector will have an amount and a unit and a direction. So the displacement, the word that we use for that, for the vector expressing a distance, we call that a displacement. That would be 300 kilometers south to get to Miami. We also have things like velocity and acceleration. Velocity might be, if you're trying to get to Miami, then you might be driving south on I-95 at 75 miles per hour. Your velocity would be 75 miles per hour south, or what is that, about 120 kilometers per hour south. Acceleration, the most infamous acceleration, is going to be negative 9.8 meters per second squared. That is the vector of the acceleration due to gravity being pulled down at 9.8 meters per second squared. Distance and displacement. When we have live class, it's easy to show this. A little bit more difficult when we have it over the internet. But imagine this in your mind. If you travel 9 meters left, think about the room that you're sitting in. It's probably not 9 meters wide, but maybe it is. Imagine traveling some number of meters left and then some number of meters right. You go, maybe 2 meters left and 1 meter right, something like that. You can calculate the distance that you traveled. That's what your odometer would say on your car. Your car's odometer tells you the distance that you've traveled. So that's the little ticking numbers on your dashboard. You can see how far you've traveled since you bought the car and whatnot. And so that's the distance that you've traveled. Your car doesn't know if you've been doing that north, south, east, or west. If you have your GPS in your phone to mark on the map where you've been going, you can find the displacement of your car. If you go 9 meters left than 8 meters right, you end up just 1 meter left of where you started. If I go from my house to my work and back, my displacement is 0. If I start here in my house and I go all the way to work and go all the way back to home, then my displacement is 0 because I've ended up where I have begun. My vector is 0. If I just go to work, then my vector would be, I don't even know. I live very close to Florida Tech, so maybe it's half a mile east if I'm going to work. And then my vector coming home would be half a mile west. And my total would be 0. My total displacement would be 0, but the distance I traveled would be 1 mile. That's the difference between distance and displacement. We're going to be working almost entirely with the vectors rather than with scalars in this class. So in general, on a test, you will need to show the amount, the unit, and the direction that something is going in, that a force is going in, that you're accelerating in, something like that. A number, a unit, and a direction. Okay, vector math. If any of this stuff, in these slides is unfamiliar, please read the book. It's sections 1.7, 1.8, 1.9, and 1.10. I do have one question. Should we have our calculators in radians or degrees? That is an excellent question, and it's going to change very, very frequently. The answer to that question will change very frequently. It depends on what the problem has. If the problem is full of degrees, something is 28 degrees in some direction, then obviously it needs to be in degrees. If you're talking about radians, obviously you need to be in radians. It is unfortunate but necessary that we switch back and forth constantly between radians and degrees. You will have to do that in your work. Anyone that's an engineer or scientist has to flip back and forth between radians and degrees. Sometimes it's much more convenient to have it in radians. Sometimes it's much more convenient to have it in degrees. I'll try to mention that and point that out when we come to some parts that it really particularly, well, it always matters, but where it's particularly tricky, I'll try to point that out. We do have this interesting vector addition computer program thing that I wanted to show. So let me get that up. That is here. You can find all these links in the slides themselves, which I posted on the files section. We have a whole bunch of different tools, different options for looking at vectors. Let's just do them one at a time. We have 3 vectors down here. You can play around with these vectors. I can take a vector and this vector A, and I can plop it down so that the tail of the vector is at 0. I recommend that you, after we're done with this, that you actually go back to this link that's in that PowerPoint presentation and try this out for yourself. You can change the length of the vector. You see up here that the length of the vector is changing. The x component, okay, the x component is 10. The y component is 0 because it's just along the x-axis. This is how we express the magnitude of the vector. The magnitude is 10. The angle is 0. We define angles with respect to the positive x-axis. So here's the positive x-axis. This thing is lying across the positive x-axis, therefore it is at an angle of 0. I can take another vector And I'm going to offset this a little bit so that it's easier to see. If I plop them down on top of each other, it'd be very difficult. So I'm going to plop it down there and make it 7, let's say, just to have something. Well, what is the, you don't have to actually answer this in chat, but I want you to think, what is the sum of A and B? If you added up A and B, what would you get? You would get 17. If this is 7 and that's 10, you'd get 17. Because this one is going 7 to the positive x direction, this one is going 10 to the positive x direction, and so together they'd go 17. We can see that by clicking the sum button right there, and it gives us the sum of the two. And if we look very closely, we can see that it lines up to 17 right there. So I'm going to put that up there so that we can see them all together. I can physically move this around and plop this down at the tip of A. So the tail of B is touching the tip of A. The tail is the back end of the vector. The tip is the part with the arrowhead. And you pick this up and you can see, oh, it perfectly matches up. The two vectors added together is the same as just taking a vector and plopping it down like that. And then you just get the total vector like that. Let's see what we get when we move on to the two-dimensional version of this. I can take a vector and put it somewhere, like there. I usually try to make it so that it lines up with the 0 point right there. And I can move it around. I'll move it like that. I'm just doing it randomly. Well, this vector is a lot more complex, I think, than the other one, because it's not just going in one direction. It's going in, well, it's still going in one direction, but that direction is made up of some x and some y. Well, what does that mean? I can actually break this up into how much x it has and how much y it has. You can see that up here. AX is 38 and AY is 13. Let's see where that matches up here. It goes from 0 all the way up here, but the x amount is 38 right there. Okay, and then the y amount, you look all the way over here, is 13. You see it goes to 38 and 13. That would be the coordinates of the end of it. I can click this button over here that will show me the components of this vector. You can see this y component there going up to positive 13, this x component over there going up to positive 38. As I move this around, the x and y components change, showing the amount in each direction. One way you can think about this, if I have my coordinate system like this, and I've got some vector like that, I can imagine a very bright light up here shining down. Imagine that, a very bright light way above the, way up at y equals positive infinity, shining down. This vector is going to cast a shadow that would look like this. The shadow it would cast would be like this. That it's difficult to see because, you know, webcam and all that, but it would cast that shadow. That is the x component of this vector. The y component is as if you have a very, very bright light all the way over here at x is equal to positive infinity. That's going to shine a light like this. It's going to cast a shadow like this, so that the height here is the same, and the other shadows from that length there being the same. That's how you can think about vector components, the x component and the y component. I recognize a lot of you have seen a lot of this stuff before in your math classes, and that is fantastic if you've seen it before in those classes. It's just so important that I wanted to talk about it again. We have this vector, vector A, I'm going to make it a little bit smaller because I'm going to add another vector, vector b. I'm going to make like that. I'm going to turn off the components right now, and something like that. Well, this vector a is going to have a total length of, it looks like 14 in the x and 3 in the y. B is going to have a length of, it looks like 12 in the x and 17 in the y. If I go over here and find the sum of those, it gives me this gigantic vector. You've added two vectors together to get that gigantic vector. How do you figure out the length and the components of this vector? One thing you can do graphically is you can, when you're working with vectors on paper, you can imagine taking one of your vectors, physically lifting it up, and plopping it down like this, so that the tail of one vector hits the tip of the other vector. Now, we can do that without having that sum right there. If you literally just take one vector, you leave it on the origin, you take the other vector, you put the tail of it at the tip of the other one, it's going to make a shape like that, and then you add in the sum, you get some vector, but it's the same as starting at the tail of the first one and going to the tip of the second one. And then as I move this around, that actually continues on, which I think is pretty neat looking. You can even have vectors that go back like that and get some negative components in the x in this case. Well, that's adding vectors. You can even take a third vector and add a third vector in. So this automatically went negative like that. You can take this vector, you can attach the tail of that one to the tip of the last one there, and lo and behold, you again get the situation where it just connects like that. Very nice. You can have an infinite number of vectors in here, and then the sum, you will always be able to calculate the sum the same way, graphically like this. And so you can take, any number of vectors and create this final S vector that way. There's actually some more stuff that I wanted to talk about this. You kind of reminded me to talk about this stuff. Let's look at the components of each of these vectors. This is kind of messy, but if you start everything off like that, I'm going to get rid of the sum right now. You start everything off like this. I'll make it like that. Start it off like this. Look at the components of each vector, which you can kind of see here. I strongly recommend that you actually play with this on your own time, because it is pretty neat. You can still take your vector and you can plop it down so that the tail of one vector touches the tip of the other vector. And we know that, okay, we've got the sum vector like that. But what you can also do is you can take this, keep it at the same height, keep it at the same y value, and move it all the way across like that. And you get this component, this y component, plus this y component, the y component of b plus the y component of a. You can also do that down here, to keep it at the same distance away in x, and now you get that x component and that x component. Well, if I very carefully just move it up without moving it to the side, you can see, if I could do that right, that this part right there didn't change. It should have stayed at the same value at about 26, it looked like. And then this over here, if I can just move that laterally across, it looks like that one ends at 21. So if you then take the sum of it, well, the sum is going to have a y value of 21 and an x value of 26, because that's the two y component values added together and the two x component values added together. And you get this final amount, which is just the x components added together and the y components added together. The x component of S, the sum vector, is going to be the x component of b plus the x component of a. The y component of the sum vector is going to be the y component of b plus the y component of a. This is going to be how we add vectors. Vector components in two-dimensional space or higher dimensional spaces, 3 dimensions, whatever. You can take any vector and you can break it into the components. That'd be the x component and the y component usually, although we will at some point talk about a tangential component and a radial component, things like that. To find vector components, you need to remember SOHCAHTOA. Oh, SOHCAHTOA. This is something that you might have to look up in your old math books or something like that. SOHCAHTOA stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If you can't remember all that stuff, just write down SOHCAHTOA and look that up in your old math books or just on the internet, actually, and you'll see what we're talking about. But it's just a way of remembering what's sine, what's cosine, and what's tangent. I have this example problem. Salt Lake City streets are on a grid system, and it really is beautiful, this grid system that they have in Salt Lake City. All the streets are either north-south or they're east-west, and the names of the streets are actually the coordinates of those streets. I can tell you my very old address there, it doesn't matter anymore. I used to live at an address that was 311 South 1000 East. That means that I lived on the street called 1000 East, and that street was exactly 10 blocks east of the center of town, and it was just south of 300 South. I lived at 311 South, so it was just south of 300 South, which was 3 blocks south of the center of town. So your address is literally your coordinates in Salt Lake City, which I think is fun. It's great to find your way around the city. So let's say I start at my own house, and then I travel 9 blocks west and 3 blocks north, and each block is exactly 1/8 of a mile. Then I cut through a park, traveling 0.35 miles exactly northeast, ending at my friend's house. I climb to his roof and can see my own house from there. Because I'm a nerd, I want to shine a laser on my own house, because that's what nerds do. In what direction should I aim my laser, and how far will the laser travel to get to my house? This is an example problem that I actually showed on one of the videos that I've uploaded. If you go to the future videos in this slideshow or the ones that I already have on YouTube, you'll actually see me solve all of this there. You can go ahead and look at that. We're going to solve it right now also, just for completeness, so that you can ask questions if you need to. And we've got, let's see, we start here. We go 9 blocks west. We go 3 blocks north. And we go 0.35 miles exactly northeast, and we end up there. And I want to know how far it is from there to there. And oh, it's all blurry. Let's see. Sometimes when I put random things on the sides of the screen, there we are. Okay, so 9 blocks west, 3 blocks north, 0.35 miles northeast. So 9 blocks, 3 blocks, 0.35 miles. If you want to find d, the distance, and theta, the angle that you have to travel at to get back home, what you need to do is take this 9 blocks and this 3 blocks and convert that into the number of miles, number of kilometers. We have mixed units here, and we need to get everything into the same kinds of units. So the 9 blocks, well, I said at some point that a block is 1/8 of a mile, so this is 9/8 of a mile. This must be 3/8 of a mile. And we have 0.35 miles up there. I said that it's exactly northeast. So that means that this angle here is 45 degrees, or pi over 4 radians. If you'd rather work in radians, then that's fine. I might ask you for the answer in degrees instead of radians. But generally, I'll accept I guess I would accept either if we had live classes, but you'll have to do whatever Canvas tells you to do on the tests. If we want to find out that distance and that angle, the distance we can find with the Pythagorean theorem, square root of all the x stuff squared plus all the y stuff squared. You can see that if you make this into a triangle, like that. If you make it into that kind of triangle, that's a right angle right there. This is one side, this is another side, this is the hypotenuse. This side, actually let's go with this side first. This side is going to be made from this side right there, that amount minus this amount. If I go this far this way, and then I backtrack that far that way, I'm backtracking here. I'm kind of going the wrong way while I'm going across this, so I'm backtracking a little bit. Backtracking. This vector up here has two components. One of them up like that, one of them east like that, but this component was west. So I go this far in the negative direction. Usually we call that way negative, that way positive, that way positive, that way negative. So east is positive, north is positive. Positive could be going to the right, it could be going forward, things like that. If we can find out the total x and the total y of all these three vectors added together, we can square each of those totals, take the square root, and that'll get us the total distance. Can anyone type into chat what we need to do to find the angle theta? Does anyone know? Hey, there we are. Inverse tangent. Theta is going to be inverse tangent of y over x. So what we need to do is find what are these x and y things that we need to deal with. And that I have on this paper, which is, it's already online. I already have a video about it. Let's look through this. The 9 blocks that we're going west is 9/8 of a mile, or 1.125 miles. The 3 blocks north that we're going are 3/8 of a mile, or 0.375 miles. And then we've got this 0.35 miles that we're going there. If we look at the x components to this, then, okay, this definitely has an x component right there. This definitely does not. Going north has no x component. So the x component of this is 0, so we can completely ignore that. And then going back this way, we've got some x and some y that we're dealing with. If we take the amount of x that we've got here, and I'm making it negative 1.125 miles, plus 0.35 miles times the cosine of 45. So that's going to be this component in there. That's going to give us negative 0.8775 miles. Now, why on earth did I pick cosine of 45? Where did that come from? That's where we have to remember SOHCAHTOA. SOHCAHTOA tells us that, let's see, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Well, let's zoom in on this right here. We're looking at this triangle, trying to figure out the components of this triangle. We're trying to figure out the x component of that triangle. That's this component right there. Well, this is adjacent to our angle. Here's our angle that we're looking at. We are looking at a side that is adjacent to that angle. This is the opposite side, this is the adjacent side, and this is the hypotenuse. So we're looking adjacent to that angle. If we're looking at adjacent, then SOHCAHTOA says that we should look at the adjacent over the hypotenuse. So that means that we can say that the x component of this, the x component of that, x component should equal the total length of that, 0.35 miles, times the cosine, because this is the adjacent side, of this angle, 45 degrees. We can do the same thing with y. And y, you see here, okay, that's not adjacent to anything. It's not opposite of anything. But I can always imagine picking this up and plopping it down over there. This is going to be the same length as that over there. And this is the opposite of that angle. This over here is the opposite of that angle. Therefore, opposite over hypotenuse means that we need to use sine. So the y is going to be 0.35 sine 45 degrees. Usually this is going to be the case. In almost all cases, we're going to have the x be cosine and the y be sine. It's not a bad idea to memorize that as kind of the default in this class. There will be exceptions though, and we will talk about those exceptions when they happen. But in general, x is going to be cosine, y is going to be sine, as long as you're measuring like this. We always try to measure with respect to the positive x-axis. Always, always, always try to measure from the positive x-axis, and then you'll get this right. If you're ever measuring from an angle that isn't at the positive x-axis, then things are going to get weird. Well, right now, all we're trying to do is find the components of this little segment. Right now, I kind of got a little bit off track. I wanted to show why we were taking 0.35 times the cosine of 45, like where that came from. And so where does that come from? Well, the 0.35 cosine 45, that is the x component of this, or on the big one, it's the x component of this length that you're going. And so we need to ignore everything else on the sheet and just focus on what's going on up there. We went west by 1.125 miles, so west gets a negative. This component is east, so that gets a positive 0.35 cosine 45. And you ask your calculator what that means, and you get that, you add them up and you get negative 0.8775 miles, which makes sense. You would expect to get a negative amount because you do end up further west than where you started. If you started there, you're definitely going to end up farther west than where you started, and we're defining west to be negative. You can do this again with the y components, where, okay, does this have a y component? No, this is all in x. This is all happening in x. So you can completely ignore this when you're calculating the y. We've got some y there. This is definitely y. You're going north when you go along that segment. And then you're going somewhat north and somewhat east when you're going on that segment. So these two segments have something to contribute. You can always say that this is actually 0 plus all that, because this part had nothing to contribute. So you can always think about it as 0 plus the rest of that. But we've got the 3 blocks north. 3 blocks we decided was 0.375 miles, so that goes there. And then we have to figure out what the y component of that vector is. So going back here, we already talked about this, but we can always take this, reposition it over there so that it's easier to think about, because you can make a triangle out of it when you do that. Just pick it up and plop it down there. And then that's now the opposite. We ignore everything else happening on the page. We say this is the opposite side. And so opposite is sine. And so the y component is going to be 0.35 times the sine of 45 degrees. So we include that there, 0.35 sine of 45. We ask our calculator what that makes, 0.6225 miles. Then, to find the distance, we suddenly have our giant triangle, right there, where this side is this counteracted against that. This is the positive one. This is the negative one. So this is actually just mostly negative. And then we've got this, let's see, we've got this amount here in y that we've got, plus this little amount right there in y that we've got from this component. So this is that side, and this side is this counteracted with some of that because they're going in opposite directions. We have this, the y component, the x component, and we can take the x component there, square it. Squaring it gets rid of the negative sign. You can just drop the negative sign, actually. When you're putting things into the Pythagorean theorem, you can just drop the negative sign and say, okay, 0.8775 miles, square that, and then 0.6225 miles, square that, add those together, take the square root, you get the distance that it would take to get back home. The angle, as you said, is theta is equal to inverse tangent of the whatever the y component is over whatever the x component is. Always remember that. Inverse tangent of y thing over x thing. These are distances. I could give you velocities, I could give you accelerations, I could give you forces, I could give you momentums, momenta, any of those. To find the angle that you're working with, it's going to be the y component of the result over the x component of the result. You ask your calculator what you got, and you get negative 35.35 degrees. That is going to be this angle here. You draw an imaginary x component or x axis there, and you get negative 35.35 degrees, which puts you down there. Now, if I instead wanted to be measuring with respect to home, like if I wanted to shine a laser from home all the way up to where my friend's house is, I would need to find this angle, like that, going from the positive x-axis around. For simplicity, I'm going to generally try to measure things from the positive x-axis going counterclockwise. Positive x-axis, go counterclockwise from there. It's always more convenient to do it that way. This is why I had to memorize the unit circle. Remember memorizing the unit circle and how annoying that was? Well, there's actually a purpose to it. And that purpose is to be able to just measure things consistently and easily like that. So if it's negative 35 degrees that way, then to go this way, it would be negative 35 plus 180. Sometimes you're going to have to add 180 to some of the angles that you get. And what you should always do, whenever you have any problem with angles in it, definitely draw it as best you can to be accurate. Use that information that you got when you're memorizing the unit circle and write that down and draw that out whenever you have an angle that you're working with. And then if you have a problem where you're having to find the angle from your house all the way up there and your calculator says negative 35, you can look at this right there and say negative 35 is definitely wrong. Negative 35 is that. Oh, wait, but if I add 180 to it, I'd get exactly what I think that I should. So always remember that. Always draw out all of your angles whenever you can. And remember, if you ever use this inverse tangent thing, sometimes you have to add 180 or subtract 180 from it to get the actual angle that you're looking for. You can kind of see this line. If you just continued this line, it'd go right through there. If I could draw it better, it'd go right through there. So in a way, this line is the same as that line, but it's just really awkward to express it as like a negative degree. So go ahead, add 180 to it, and if you're looking at the angle from your house all the way up to your friend's house, like that. This video actually goes through everything that I just did, so you can refresh yourself with that. Here's all the work that I just showed you, so you can look back on that whenever you need to. This works with any vector, as I said. We've been working on it with displacement, but you can use it with velocity, you can use it with acceleration, force, momentum, anything. So let's look at it with a vector version of it, a velocity version of it. In the Nevada desert, you are Naruto running at 19 meters per second in a direction 105 degrees counterclockwise from east. Remember that meme? That meme is pretty much dead. How should I set up my equations to find the components of your velocity? I give you all these options right there. I say that you're running in a direction 105 degrees counterclockwise from east. 105 degrees counterclockwise from east. That's how we've been measuring our angles. East is the positive x direction. Counterclockwise is the direction you go around the unit circle. So we actually already have it in the format, the exact format that we would need. And let's see, is 105 degrees the angle, or is 19 meters per second the angle? Pretty sure that 105 degrees is an angle and 19 is the velocity. So do we ever put velocity in a trigonometric function? Probably not. Yeah, pretty sure the 105 should be inside the trigonometric function, and 19 should be outside the trigonometric function. Yeah, good. So we need the 105 as the degrees, and then we need to figure out, okay, do we need the sine for north or the cosine for north or what? Well, north is traditionally y, and we said in the previous part that y is going to be sine and x is going to be cosine. In pretty much every situation that we're going to deal with very few but very important exceptions, you're going to have the sine being y and the cosine being x. So that means that this first one, the yes, has to be the correct answer. Got that right there. And what do we do if we get those answers? Let's say we type this into our calculators and we got those as answers. Negative velocities are totally fine. It is totally fine to have a negative velocity. That just means that you're going backwards, or you're going west, or something like that. So yeah, you can definitely have negative velocities. Now, if you just took the absolute value of these, then you would lose the fact that you're going a little bit west. If you go 105 degrees counterclockwise from east, then you've gone past north. North is 90 degrees counterclockwise from east. So 105 degrees is an extra 15 degrees off of north, going now a little bit west. If you took the absolute value of this, you would end up getting two positive values. And you know that if you have a positive x and a positive y, then you're in the first quadrant. But that's not where you're actually running. You're running in that second quadrant. You're going a little bit west because you've gone 105 degrees, which is more than 90 degrees, counterclockwise from east. So you can't just take the absolute value. Let's see, a negative velocity east means you have a west velocity component. Yeah, that's true. A positive velocity north means you're heading exactly south. No, that's nonsense. Negative velocity east means you have a west velocity component. That is correct. Let's verify this. We've got negative 4.92 meters per second as Vx, or we can think about it as 4.92 meters per second west. We've got Vy is equal to 18.4 meters per second, or we can call it 18.4 meters per second north. Now, this question I always ask every semester, do we think in north, south, east, or west, or do we think in plus or minus Vx and Vy? And I'm actually surprised by the answers that I get. I have a lot of students that say that they think in terms of oh, just positive Vx or negative Vy, things like that. And that's fine. That's actually compelling, and that's useful for many people to think in terms of positives and negatives. That's a very mathematical way of thinking. Personally, I think in north, south, east, or west. This is what goes through my brain. I don't think that I'm going, if I'm driving down to Miami, let's say, I think I'm driving south. I do not think I'm driving with a negative y velocity component. Yeah, the signs on the highways say, yeah, Miami is 300 kilometers south of here. They don't say that you need to have a displacement of negative 300 kilometers in the y direction. I prefer thinking in north, south, east, and west. It's okay to not like that, but I think it's vital for everyone to be able to convert back and forth between these kinds of concepts. I strongly recommend that you sit down with some graph paper, perhaps, and a map, and just think about, okay, these are y, these are x, these are positive, these are negative, and think about, you know, things going forward, that's positive, things going backwards, that's negative. Right, we're going to define as positive, and left we're going to define as negative, because that's how it looks on a Cartesian coordinate plane. How do we find the magnitude and direction of this velocity? We've actually already talked about this. Magnitude is going to use the Pythagorean theorem on those velocities. On these velocities, you can just take the x component and square it. That'll get rid of the negative. The y component, square that. There's no negative to worry about. Take those, add them up, and take the square root. That's the Pythagorean theorem right there. And the direction is going to be the inverse tangent of y over x. That's how we figure out the magnitude and direction of this final, of these components. If you do that, and I encourage you to actually do this on your own, do that. Use the Pythagorean theorem to find the resultant magnitude of the velocity, and use the inverse tangent to find the direction of this. You're going to find that the magnitude of the velocity is correct. You'll find that the magnitude really is 19 meters per second. You'll find that the direction is going to be some weird negative number, because again, things that end up being in quadrant 2 and quadrant 3, the inverse tangent doesn't quite know how to handle that. If you're in quadrant 2 or quadrant 3, the inverse tangent is probably going to lead you wrong. And so you have to remember to add the 180 degrees to that. All of this is in the physics book in section 1.7 through 1.10, I believe. So go ahead and read that if you're confused by any of this. That's what I say here, that be careful with these negatives. If you actually plug this into your calculator, you'd get negative 75 degrees, which is definitely not positive 105 degrees. So draw what you're doing and then choose to see if you need to add 180 degrees or not. If you're in quadrants 2 or 3, you're going to have to add the 180 degrees. There are many ways of expressing components, and I list some of them here. We have this kind of bracket notation, where we have the x component, negative 4.92, and the y component, 18.4. And then the units, we usually just leave outside because it's more convenient to write it like that. Saves a little bit of time. You can have the x and y components in a line like this, or one on top of the other. The x component goes first, then the y component. There are other ways of expressing components. It's negative 4.92i plus 18.4j meters per second. I, this bold I, is usually used for the x direction. The bold j is usually used for y direction. X hat and y hat. This PowerPoint doesn't let you actually put the little bracket looking thing on top of it, the little hat on top of the letters, so I just had to write it like this. That's another way of saying the x component and the y component of a vector. The way we've been doing it here is saying Vx is equal to negative 4.92 meters per second. So we explicitly say the x component of the velocity, the subscript x means x component of the velocity is that. The y component of the velocity is that. This is probably the clearest way. This line, Vx is equal to whatever, Vy is equal to whatever, that is the clearest way of talking about vectors, because you're very specific. It's the x component of the velocity that you're talking about, or the y component of the velocity that you're talking about, and you spell it out very specifically. I like this format. I also like 19 meters per second at an angle of 105 degrees counterclockwise from east. This takes a while to say, but it's telling you the magnitude and the direction all right there. I'd say these last two are the best ways of expressing vectors. Use the previous few slides and your book to get practiced on converting back and forth between this component version and this magnitude and direction version. I give you several homework questions where you have to do this. Each of these, as I say, is useful in its own way. I have underlined the ones that I think are the best ones. I also think this one is pretty good, but these last two are going to be the ones that we use the most in this class. We can also add vector components together. If we break it up into these bracket formations, so that these are two different vectors. I'm saying we've got two vectors, this vector with an x component of 4 and a y component of 8. We're adding an x component of 2 and a y component of negative 3, a vector with those components. Well, to get us to the resultant vector, you just take this 4 right there, add that 2. This is the x component. The 4 is the x component of the first vector. The 2 is the x component of the second vector. You add them up, and what do you get? You get 6. Then for the y components, you take 8, which is the y component of the first one. You add negative 3, which is the y component of the second one, and you get 5. And often you can just leave vectors like that. If I ask you for the x and y components of the resultant vector when you add these two together, you can say, well, the x component is 6 and the y component is 5. Maybe I also ask you to figure out the magnitude and direction of that. So the magnitude would be 6 squared plus 5 squared. Take the square root of the whole thing. The direction theta would be the inverse tangent of 5 over 6. And just ask your calculator what those are. This is that link to the exact same thing that I was showing you before. So go back and look at that link and play around with all the things that you can do on that link. I think that it's very, very useful. If we want to multiply a vector by a scalar, well, it's not too hard to do that. Let's say we have a 3-dimensional vector. I'm going to say the vector A is equal to 2, 3, 4. That means it has an x component of 2, a y component of 3, and a z component of 4. This would be the vector coming out of the page. You draw a regular vector with an x component of 2 and a y component of 3, and then you pull the tip of that vector out of the page by 4 units. So that's a 3-dimensional vector right there. If I asked you for what is 3a, 3 times the vector a, well, you just say 3 times the vector a, and then you can distribute this 3 through each of these. So you'd multiply the x component, which is 2, multiply that by 3. You take the y component, which is 3, multiply that by 3. You take the z component, which is 4, multiply that by 3, and you get 6, 9, 12. The x component, the y component, and the z component. Later on, we're going to talk about how to multiply a vector by another vector. We should not be doing that yet. Eventually, we will be doing that, and we will learn about dot products and cross products, which are also known as scalar products and vector products. We're not doing that yet. The book actually talks about that a little bit in, I believe, the last section of chapter 1. So you can go ahead and read that and get a little bit ahead. It's useful, but we will not be dealing with it quite yet.